All right, so good morning, guys. Today we're going to start talking about a pretty challenging concept when it comes to differentiation or derivation, and it's called implicit differentiation. And this is a little tricky, so you guys are going to need to take some good notes along with me today. We're going to do several examples, but we'll model it. There's going to be a little bit of follow-up practice on it tonight, and then when I come back tomorrow on Wednesday, we'll be able to go through and do kind of like a recap and a discussion of the homework. So our essential question is, can the learner demonstrate fluency and accuracy in the computation of the derivative of what we call an implicitly defined curve? And these are pretty common and prominent when it comes to them asking you questions on the AP exam. You're going to have some equations that are implicitly defined curves where you're asked to find the derivative. So that's what we're modeling today. So just some general information here about this idea. Implicit differentiation allows you to find the derivative of y with respect to x of a curve without having the equation solved for y. That's very different for us so far. Big rule that's going to be in play today, we'll use it all the time when we're doing implicit differentiation, is the chain rule. This must be used whenever the function y is being differentiated. So anytime you're deriving a term involving y, the chain rule is going to be in play because of our assumption that y may be expressed as a potential function of x. So, in other words, red right here, every time you derive with respect to y, you must multiply that derivative by dy dx, the derivative of y with respect to x. And you'll see this happening as I'm modeling examples. All rules are still able to be applied here. The product rule, quotient rule, trig rules, power chain rule, all that good stuff is still in play. Okay, so derivatives kind of build onto themselves as you learn more and more. So we're going to start just with some visuals here to kind of get you comfortable with what we mean by implicitly defined curves. Over here on the left side, you see what we call an explicitly defined curve. This is what we're used to finding the derivative of. We got y solved for right over here by itself, and this equals, and all over here is just x stuff. So, when we find this derivative, we don't have to really worry about this implicit differentiation stuff because we just go power rule. That'd be 3x squared minus 8x. Over here, however, you see your first example of what we call an implicitly defined curve. You'll notice that y is not solved for in this curve. It's kind of mixed in over here with some x's. It's got an exponent right here. It's got some stuff going on with it. So when you've got a curve of this nature, then you've got implicit differentiation in play. Notice I keep saying curve. We don't call these functions because we don't know if this passes the vertical line test or not. So it's not fair. It's not accurate to call this a function because we don't know. It could be a function, but we don't know. So we just refer to it as curves. Okay. This is actually going to be our first derivative that we look at, this x squared y cubed minus xy equals 10. We're going to find the derivative of this curve. Okay. Take you a second to write this problem down. Don't have guided notes today, so you'll just be writing these down and then seeing me derive them with you. All right, so first thing I want to point out in this curve is that as we begin our derivative, we want to notice that there's a product rule right there between those two terms, the x squared and the y cubed. And then there's also a product rule right there between that x and that y. Okay, so you're going to see some product rule kind of stuff happening here. All right, so as we bring this down, we're going to have the derivative of the first. The derivative of x squared is going to be 2x times the second plus the derivative of the second, which is going to be 3y squared. And here's where we've got to give. We just derived with respect to y, so we've got to attach a dy dx to that. Every time you derive a y term, you attach with the chain rule a dy dx. So that's the derivative of the second times the first. Okay, and let's pause for just a second. We've just done, put a little check mark, that first product rule. Derivative of the first times the second plus the derivative of the second times the first. Okay. We're going to go minus, and then I'm going to put a big old set of brackets around this. And the reason I'm doing this is so that we correctly distribute this negative across our sum, which is getting ready to be created with our product rule. All right. So we've got the derivative of the first would be 1 times the second plus, all right, so the derivative of y would be the same as the derivative of x. It's just 1, but we've got to attach the dy dx to that. And you'll start to get into the habit of, I wrote the 1 here, but you'll get so comfortable with deriving just y that you'll just call that dy dx. It's the derivative of y with respect to x. So that's derivative of first times the second plus the derivative of the second times the first. And this is going to equal, this is a nice and easy piece, the derivative of 10, well, that's just 0. Okay. All right, so here is now our objective. Our objective now is, now that we've got this raw form of this derivative, we want to isolate this derivative so that the dy dx is solved for. Like our answer at the very end is going to say dy dx equals blah, this. Okay, and that's our objective. Figure out what that is. So the first line of work that I'm going to do is just, kind of like a cleanup rule, or cleanup line of work, I should say. We'll just call that 2xy cubed plus, that's going to be, let's call that 3x squared y squared dy dx. And then I'm going to make sure that this negative, switch colors there, this negative has got to go to both of those. That's why I put this in brackets, so that I would kind of remind myself that that negative goes to both of those terms right there. So this is going to be a minus y and a minus x dy dx, and that equals 0. So you'll notice that we've got two dy dx's in play here. And so, it's the question you might have right now is, how do I turn those two into just one? And we'll see that happen. We're actually going to do so via a GCF, but we're not quite ready for the GCF. I'm going to take this term right here and this term right here, and I'm going to move them to the other side of the equation. I'm going to subtract the 2xy cubed, and I'm going to add the y to both sides. Add the y, subtract the 2xy cubed. So we're moving the non-dy dx terms to the other side. And what I'm going to do in my next step is, as I'm bringing this line down and this line down, you're going to notice I'm going to go ahead and factor out the GCF. Now there are some other terms that are in common. They both have, they both have an x, but you do not need to pull that out, just the dy dx. So that leaves us with 3x squared y squared minus x, and that equals what I'd move to the other side. I'm going to write that positive term first, y minus 2xy cubed. And so to solve for dy dx, we're going to divide out the 3x squared y squared minus x. 3x squared y squared minus x. And we're ready to kind of provide that final derivative. The derivative of this curve is y take away 2xy cubed all over 3x squared y squared take away x. We'll put that in a nice little bubble. There's our derivative found implicitly. Okay. I think you would agree that implicit differentiation can be very messy. I mean, if you just look at this, it's messy looking. So it's very important that we keep, I use parentheses and brackets to kind of keep things organized as I'm working along. Show as much work as you need. Okay. Let's clear that one. And let's do another one. Let's throw some trig in the mix here. So you might look at this initially and say, hey, this is an implicit curve. Look, it's y equals. But if you keep looking, you'll notice that, oh, yeah, well, there's a y over here too. So this is an explicitly defined curve. We're going to derive this whole thing implicitly. We're going to find dy dx. All right, so I've got a derivative right there, a derivative right here, and a derivative right here. We don't have any product rules like we had in our previous one. These are just some trig rules. So we'll kind of bring these down. I'll call that 1 and 2 and 3. Kind of match this up as we're working. So the derivative of y is going to be 1 dy dx. The derivative of the sine of x is just the cosine of x. And the derivative of the cosine of y is negative sine of y. And then here we go. We just derived with respect to y, so we're going to attach a dy dx to that. Okay, so to match that up, that was the derivative there of that first one, the derivative of our second one, and the derivative of our third one. Okay. Notice that there are two dy dx's. So if I'm supposed to just find one of them, then I need them to be on the same side so that I can factor out that GCF of dy dx. So what I'm going to do next is add this sine of y dy dx from the right side to the left side. That's going to equal the cosine of x. I'll GCF the dy dx. Careful here, that's going to leave us with 1 plus the sine of y. And then we're going to divide that 1 plus sine of x, 1 plus sine of y out. So we'll say that the derivative of y with respect to x is the cosine of x over 1 plus the sine of y. There's our derivative. So not quite as messy as our previous one. There is some trig involved. We didn't have to move a dy dx term. We didn't have to do that in our previous problem. I had to move this over, GCF that dy dx out, leaves us with 1 plus sine y, and then we divide this out right here. There's our nice derivative. Good stuff, good stuff here. Okay, so let's talk about maybe extending this a little bit into maybe not just finding the derivative, but perhaps maybe evaluating it at a point. Remember, when you find a derivative and you plug in information to it, you're finding the slope of the tangent line. So this question could be reworded to say, what's the slope of the tangent line of this curve when x is -1 and y is 1? And you'll find that here in a minute, we're actually going to need both of these values to find the slope of the tangent line. Normally we just need the x. Well, when x's and y's are both involved, you actually need the point of tangency right there. We're not going to write the equation of the tangent line. It doesn't ask us to do that. We just want to find the slope of the tangent line. Okay. So let's see. There's going to be a derivative here. We'll call that 1. That's just going to be a nice little power rule. There's going to be a derivative happening here. That's going to be a product rule. That's 3x times y. And then another little product rule right there. Power rule right there. And then this is an easy derivative. That's just derivative of a constant. So 4 derivatives are getting ready to happen here. All right, here we go. Derivative of x squared is 2x plus, and I don't really need the brackets here, but I'm going to put a bracket just to kind of organize my product rule for my second derivative. We're going to go derivative of the first times the second plus the derivative of the second times the first. There's my product rule between 3x and y. Derivative of first times the second plus derivative of second times the first. Derivative of y just being dy dx. Let's see, plus derivative of y squared is 2y. dy dx, we derived a term that was a y term, and that's going to equal 0. I'm going to grab my eraser right here. I really don't need those brackets. I just was doing that to kind of help you see. I'll go back and fix that right there. See that product kind of happening. That's plus that right there. Big old plus sign. All right, so there was our first, our second. All of that was our second, our third, and there was our fourth derivative that just happened. Kind of keep this organized for you. All right, so we're going to move the non-dy dx terms away. And in doing so, we're going to have, let's see, that's going to be 3x dy dx plus 2y dy dx equals, let's see, we're going to have both of those are going to be negative. So we'll just go negative 2x, negative 3y. That's just a moving stage right there of our work. We subtracted the 2x from left to right, subtracted the 3y from left to right. And now we're going to go GCF. Here's where we're going to get those multiple dy dx's to magically turn into 1. 3x plus 2y is negative 2x minus 3y. Okay. So we're going to divide out that 3x plus 2y there. I'll actually show that in this step. Get those to cancel, and here's our derivative. And it's super important that we get this right, guys. If we don't get this raw form of this derivative right, this instantaneous rate of change representation, then there's no way we're going to get the negative 1, 1 going in to be the right numerical value. We've got to make sure that this value is right. So we'll put a little star by this. This isn't our final answer, so we're not going to bubble it yet, but that's super important. Okay. So now what we're going to do is we're going to evaluate the derivative at the point negative 1, 1. And you'll notice that our derivative actually has both x's and y's in it. So we need both the negative 1 and the 1. So here's how we would kind of notate this. It's a little bit weird and different for you. We say dy dx, and we kind of go a little subscript down here and just go negative 1, 1. It's kind of showing what we're plugging in. So it's going to be negative 2 times negative 1 minus 3 times positive 1 all over 3 times negative 1 plus 2 times positive 1. Just substituting in the negative 1 where x is and the positive 1 where y is. Let's see what happens here. That gives us 2 minus 3 all over a negative 3 plus 2, which is a negative 1 divided by a negative 1 for a nice final answer of positive 1. There's our answer to this question. Find the derivative at negative 1, 1 if this is the curve. This is the slope of the tangent line right here. We deserve a smiley face after all this hard work. All right, let's see what we got next here. So we're going to find, let's take it a little further. Let's find the equation of the tangent line to the curve at the point 3, negative 4. All right, let's find the equation of the tangent line. Equation of the tangent line. So some of you may recognize this, some of you may not. This is a circle. This is a circle. It's centered at the origin. It's got a radius of 5. I'm an awful circle drawer, so don't make fun of my circle here. Here's our circle. We've got a radius of 5. That's 5. That's 5. That's negative 5. That's negative 5 right there. And we're finding the equation of the tangent line at the point 3, negative 4. So right 3 down to negative 4. Just a little eyeball right there. We're going to write the equation of this line right here. Nice tangent line there. So something that I can already kind of tell just from my visual that I've kind of sketched here is that my slope should be positive. And it should probably have some sort of a negative y-intercept. You can kind of see that evident there in just that little sketch. So some preliminary kind of understanding going into our work here. Okay. All right, so let's see here. Derivative of x squared is 2x. Derivative of y squared is 2y. Got to attach the dy dx. And the derivative of 25 is 0. Let's see, let's move the 2x over, so we'll have 2y dy dx is equal to negative 2x. And we can divide out our 2y. Get that out of there, 2y there. And if we simplify this down, I think we could say, that the derivative is equal to, I think we can just call that negative, you can put that negative out front, just negative x over y. Or you could say negative x over y. However you want to associate that negative, it's up to you. Okay? And we're going to evaluate this derivative at the point 3, negative 4. Let's see, I'm going to stick with that second one up there. I'm going to go the opposite of 3 over negative 4, or our slope is a positive 3/4. And we know the slope's positive, and going back up here to our little prediction of our sketch, we should get a positive slope. Okay. All right, so let's see if we can't write the equation of our line now. We've got our slope. We know the slope is equal to 3/4. We know that the point of tangency is 3, negative 4. So we can say y plus 4 is equal to 3/4 times x minus 3. And that is a 100% acceptable representation of the equation of the tangent line. Since we had talked about up here that it's got a negative y-intercept, I'm going to go ahead and take this a little bit further and Let's see if we can't maybe show that. It'd be 3/4 x, take away 9/4, and then I'm going to subtract 4 from that. So let's see, if I subtract 4 in a fourths term, that'd be 16/4. And we'll get 3/4 x minus 25/4. It's another variation there. Both of those bubbled and boxed in answers are representations of our equation of our tangent line. Okay. All right, I think we've got one more here where we're going to use the same curve, but this time we're going to find, and here we go, we keep building on ourselves, the second derivative. Yes, implicit derivation can go higher derivatives. We can find our implicit derivative, and then, hey, guess what? We can find the derivative of that derivative. So we're going to use the same curve. So not a whole lot of work involved, but still it's a little different. So let's see. Our previous one was a negative x all over y. That was our first derivative. So if I do my second derivative, d squared y dx squared, I'm going to have to follow a quotient rule. So I'll go low d high, derivative of negative x is -1, minus high d low all over the bottom squared. Raw form there of that quotient rule. Low d high minus high d low all over bottom squared. And one thing that you'll kind of notice here, and this is important, so I'm going to highlight this. You'll notice that actually the dy dx showed back up right there. Kind of right back over that. Dy dx. We cannot leave this. We are not allowed to leave the second derivative in terms of the first. So I encourage you to look up a line of work. We actually know what dy dx equals. We know that dy dx is equal to the negative x over y. So it is expected of you. I don't think this is up to you to decide. It is expected of you to make this substitution right here. Okay, we need to make sure that as we clean this up that we do substitute that negative x over y back in there. Okay? So everything that I'm getting ready to model moving forward is just me cleaning this up and not representing it in terms of dy dx. So it's going to be negative y. I'm going to go ahead and call that a, let's hold off on this right here. Let's go minus. So we got our negative x times the negative x over y. This is all over y squared. Or, let's see if we can get one more line down here. Negative y minus, the reason I held off on that first minus is because we got a negative times a negative right here. So this is going to be x squared all over y. All of that is over y squared. Sorry, I ran out of room there. Let me come up here and write this again. So right now we've got our second derivative is equal to negative y minus x squared over y, and that is over y squared. Now you might be thinking, hey, we're done, we got it. It's not in terms of dy dx, but this is not technically simplified. So just a little bit more work here. We can't leave this complex fraction. It's not formal notation or simplified notation to leave a fraction within a fraction. So here's what we're going to do. In our numerator, we're going to put that y over 1. And what we're going to do is we're going to multiply by y on top and bottom. And what that's going to do is it's going to allow us to condense that numerator into one fraction. And then we can do our outside-inside technique and kind of simplify this into just a fraction. It's going to give me negative y squared minus x squared. And that's all over y. That's my numerator. And this is all over y squared over 1. Put that over 1 so that our outside and our inside becomes very clear. So here we go. All that nice hard work. Feels rewarding to get down here and have this final answer. So outside is going to give me negative y squared minus x squared all over y cubed. Here's our second derivative. Okay. So yeah, implicit differentiation in itself is a tricky little concept. We're going to spend a couple days on this. Trust me, this is something that's, like I said earlier, it's prominent. You're going to be asked about this, and it's difficult. So um, sorry I'm not here to do this in person, but I will be back tomorrow. But I do want you to get some practice, okay? So even as difficult as implicit might be, yeah, we can take it into higher order derivatives as well, which just adds another layer of difficulty to it, unfortunately. But really cool derivation stuff going on here. Let me clear this for you. Let's scroll down and let's get a little bit of practice here. I do think it's important for you to go and get you some practice here. So let's follow this up. You probably got time in class today to do this as well. We're going page 167 right there. Got a couple randoms. I did choose all odds for you. I don't know if you guys noticed that in 167. I chose all odds so that you can kind of check your work. Also, my work is posted to Schoology. You're going to need to go up to Derivatives Part 2. It should be called something like, I think it's like Implicit Homework Key. So you can check with the book if you want to. You can, compare your work to mine as you work. But do try number 4 at the bottom on page 169. That one's even, so we'll have to talk about that one tomorrow. But let's get some practice with this, okay? Do the best you can. I'll be back tomorrow. We'll have a little Q&A session on this. I'll probably end up working several of them for you guys, but give it a shot. I'll be back tomorrow. We'll fix it. You'll be okay. Don't stress. Once again, miss you guys and can't wait to be back. Have a good rest of your day.